Hello, my name is NAVINKUMAR, son of Kumaran. My ID matrix is B1124104113. This is our control system assignment. I have done the system 1. So this is the expanded version of the transfer function as stated. These are the ports and 0 for the system. The ports are 0, 93 and 95 and zeros are none. Breakaway point, the value is negative 1.21. JW crossing point for the system is plus minus J 3.87 and the K, which is gain value, is under 20. I have drawn the root locus on the graph paper as stated. So this is the root locus. These two are JW crossing point. This is centroid, which is negative 2.67, and this is the asymptote angle, which is 60, 180 and 300. So overall this is our root locus, and this one we get from MATLAB as same as the root locus drawing. And then move on to the graph. The first one is overdamp. The damping ratio is more than 1. Settling time is 8.6 seconds. Rise time is 4.65 seconds. Overshoot 0 and peak deviation is 1. The second one is critical damp. Damping ratio equals to 1. Settling time equals to 5 seconds. Rise time 2.81 seconds. Overshoot 0. Peak deviation in 1. Undamped, no graph. And finally underdamped. Damping ratio is 0.576. Rise time 1.09 seconds. Settling time 3.58. Overshoot 10.4%. Peak deviation equals to 1.1 and final value equals to 1. So no steady state error. So this is our result when we factor our settling time by 2, which is 28.55 seconds, and this is our result. Rise time equals to 1.46 seconds. Settling time equals to 28.6 seconds. Overshoot equals to 62.4%. Peak deviation equals to 1.62. Add time equals to 4.06 and final value equals to 1. We have proof that the result from the simulation and the calculation are the same. Finally, the dot plot. This is the coding we have applied in the MATLAB, and this is our result from the MATLAB. And this is the drawing of dot plot. Determine the gain margin and phase margin for this system is gain margin value equals to 21.6 dB and phase margin equals to 17.5 degree. So we have proof that MATLAB or simulation software value equals to our calculator value. That's all from me. Thank you.
Hello, good day everyone. Today I will present the analysis and control design for System 2 using root locus and frequency response methods. This is System 2. First, for question A is poles and zeros. The poles are 0, 0, negative 0.807, negative 6.193. It is a double pole. Then total number of pole is 4. 4, 0 is S equal to negative 0.5. For breakaway point, S is equal, the breakaway is at negative 4.197, equal to negative 4.2. Then the JWS crossing point is K equal to 35, and the S plane is plus minus J 0.236. For question D, root locus sketch. This is the root locus. The asymptote is at 60 degree and 300 degree, also at 180 degree. This is the asymptote calculation. The central point is at negative 2.167. This is the controller design, and the setting time is half than the current, which is 153 divided by 2 is 66.5. The controller design is to improve settling time by a factor of 2. It's achieve zero steady state error. By turning the KP, the dominant poles are shifted to the left, which reduces the settling time. After turning the left, the settling time is reduced by half and steady state error is become 0. For G question, this is the proof that poles is 0, 0 is negative 6.1926 and negative 0.8 0.8074, and for 0, negative 0.5. This is the root locus. For question C, this is the proof. The forcing point at negative 0.236. This is the root locus sketch. For E, the overdamp is no values, critically damped no values, and the undamped is no values because the damping ratio is the biggest is 0.0851. So for overdamp, it should be the damping ratio, it should be over 1. So if no over 1, so no graph. For critically damped is equal to 1. Just now I said the damping ratio is until 0.0851, so it's not equal to 1. For undamped 0, there is no damping 0, zeta is equal to 0. So for underdamped, the gain is 1.969 and the damping ratio is 0.0851. So the overshoot is x7.3, take length is 97.9, time is 2.05, and the final value is D. This is the board plot sketch. The gain margin is 0.424 dB and phase margin is 0.443 degree, and this is the proof that the board plot. That's all from me for system 2. Thank you.
Hi, my name is RAVINKUMAR. Today we'll be discussing about control system. For me, I got group 4 system 3. So what I can do is from here, since this is a quadratic equation, we can factorize it. So once we factorize it, I'll get s plus 2 plus 6. So I can eliminate 0. So that if I eliminate 0, the system, I can create the system more efficient and all lah. So yeah, so I get 0, none. Here it shows 0 because because it won't eliminate 0 by using the calculation theory. So that's why I use GS simplified, G3 simplified, so that it can understand we using this the title. I mean this transfer function, the simplified transfer function. And then for part B is, so we can find for the breakaway points, as you know, are defined negative 1.2, 1.81, negative 5. This one negative 5.52 also. So this one I try to reject, and then this one is yes, because I'll explain when it comes to part D. And then part C, we use the root table, and then I try to find K is 330, and then for the S is J imaginary 5.48. So here, if I use K30, the gain margin, so I can get the S value, as you can see. It's proven. Then this is the graph. So here the centroid is 3.67. This is why just now earlier when in B, I rejected the negative 5.52. So this is why I only take negative 1.81. And then since here 5.48, 60, 80, 30. Here we do the calculation here. And then this is for the root locus as we calculated, as we get for the MATLAB. And then for part E is about the graph. We got the breakaway point negative 1.81. So I try to find the critical value, which is in the formula, right? So since I can get 24.2, so I try to manipulate it by it, play by it. So K over dam everything. So I just choose, because less than 24, it must be over dam, right? So I choose 10, then correctly I get over dam. Then on critical dam it's 24.2, correctly on there. Then I simply choose 100, so and it became under dam. Then when I choose 250, it became under the undam. So it's all in correctly in order. And then for the design, I choose 50 because more than 24.2 critical dam, it should be the perfect one for the, because usually the damping damping is will be 0.5 right, natural damping. So that's why I choose this design 50. So here this is why I use PID for the newer system, and I use 20 because you will eliminate faster. I can get a faster exponentially 2 times faster, as the question said. So yes, I get 2 times faster from here. And then this is the dot plot diagram. I get 30 and 30.4 dB and 83 degree. I think that's all from me. Thank you.
Okay, my name is RAVINRAJ and PRAGASAM. In this assignment, the behavior and stability of 3 unity feedback control system were analyzed using root locus, time dominant response, the frequency dominant methods. The open loop poles and zero were identified to understand how the system dynamics change with varying gain. K-root locus plots were used to determine breakaway, break-in points, imaginary exit crossing, and suitable gain ranges for overdam, critically dam, underdam, and undammed response. MATLAB simulation verified the theoretical result, showing clear relationship between gain values, damping ratio, and transit performance such as rise time, settling time, and overshoot. Control design was implemented to improve the settling time by a factor of 2 while maintaining zero steady state 0. Demonstrating how comparison can enhance system performance. In addition, both plots, gain margin and phase margin analysis provided insight into frequency response and relative stability, confirming the robustness of each system through simulation results. Next, conclusion. In conclusion, this assignment has fully demonstrated the application of control system theory and analysis and improve dynamic system performance by combining analytical method with MATLAB and simulation. The stability characteristic and transit response of the given system were clearly understood and validated. The root locus technique proved effective in selecting plotted gain value and predicting system behavior, while frequency domain analysis confirmed system robustness through gain and pace margins. The design controller achieved the required improvement in settling time with zero steady state error, meeting the design objective. And overall, the result highlight the importance of both critical analysis and simulation tool in control system energy for accurate modeling, validation, and performance exchange. That's all. Thank you.